Welcome. Today we are going to learn about the mathematics of the growth or mathematical expression of the growth. Before that, what do you mean by the growth? Growth may be defined as increase in cellular constituents. It leads to rise in number of cells when microorganisms reproduce. Here particularly the bacteria. The bacteria, it is going to divide by the binary fission. Okay, and when it is going to divide, the cell number, it is going to be increase. So when you are concerning about the microorganism, at that time the growth it is going to be measured in the increase in the cell number. Growth also results when cells simply become longer and larger. Here, some of the microorganisms which are the co-inocytic, okay, that is the multinucleated organisms in which the chromosomal replication is not accompanied by the cell division. The growth it is going to be result into the it is going to result simply becoming a longer or the larger cell, and this it is going to be observed in some of the fungi. Now going towards the mathematics of the growth. Now in the mathematics of the growth, here you are going to calculate for the generation time and you are going to calculate about the growth rate constant. Okay, so the growth rate studies, okay, contribute to the basic physiological and the ecological research and are applied in the industries. So when you go for the industries, when you go for the fermentation industries, in the fermentation industries, here you have to apply these mathematics of the growth, that is the generation time that you are going to calculate or the growth rate that you are going to calculate. It is going to be applied when you are going to design the fermentations. Okay, here the most common method of the reproduction in the bacteria, it is a binary fission. Just we have seen that. So here when one cell divides, there is the production of the two cells. Now here the one cell, when it is going to divide by the binary fission, it is going to produce the two cells. Two cells when they are dividing, it is going to produce the 4. The 4 it is going to produce the 8. 8 it is going to produce the 16, and the 16 it is going to produce the 32. And this it is called as an exponential growth. That is, there is an increase in the cell number. Okay, and the increase in the cell number, it is at a constant interval. Now here, during the exponential phase, each microorganism is dividing at a constant interval. Okay, and the population, okay, population doubles in number during a specific length of the time called as an generation time or the doubling time. Okay, now here it is the graphical representation of the exponential microbial growth. Now this graph, what it is going to suggest that there is the increase in the cell number, okay, and the cell number it is going to increase in this fashion. One cell divided, then it is going to give the two cells dividing the four cells dividing into the 8 cells. That is, there is an increase in the cell number, and every time there is a doubling of the cells. Okay, this it is going to represented by this graph. Now here the graph, in this graph on the x-axis there is a time of incubation in the minutes, and here it is the x-axis, sorry, it is the y-axis, and y-axis it is representing the number of cells and the log number of cells. So here, when the graph it is plotted incubation period against the number of cells at that time, in this fashion you are going to observe there is a graph, and here also you can see that there is an increase in the number of cells. Okay, the cells they are going to doubling. Okay, but when you are taking the log of this number of cells and plotting it, and the graph it is now how the minutes of incubation against the log number of cells, then what you are getting a straight line. Now here there is taking of the 4 generations, and in this 4 generation what you can observe that after every particular time interval, okay, there is an increase in the cell number and there is a doubling of the cells. Okay, there is a doubling of the cells. That is, this graph it is going to represent what? Exponential microbial growth. From this graph, what you can see that the population is doubling every generation. This increase in the population is always 2n, where n is the number of generations. Now, this observation can be expressed as equation for the generation time. So here, N0 is equal to initial population number, NT it is the population at time t, and N is the number of generations in time t. The equation it is a NT is equal to N0 into 2 raised to N. Okay, so NT the population at time t, N0 it is the initial population and N it is the number of generations in time t. So here solving it for the N. So 0 log of NT is equal to log of N0 plus N log of 2. Okay, now we have to solve it for N. That's why N is equal to log of NT minus log of N0 divided by log of 2. The log of 2, it is the 0.301. That's why log of NT minus log of N0 divided by 0.301 is equal to N. Okay, by this equation, what you can calculate? You can calculate the number of generations. The rate of growth during exponential phase in a batch culture can be expressed in terms of the mean growth rate constant, that it is the K. And this growth rate constant is number of generations per unit time, often expressed as the generations per hour. So here K is equal to number of generations divided by the time, that is a N by T. Now just now we have seen that the N is equal to log of NT minus log of N0 divided by 0.301. So this value it can be substituted in this equation. So the K is equal to log of NT minus log of N0 divided by 0.301 into T. So by this equation, what you can calculate? You can calculate the mean growth rate constant, that is the K. The time it takes a population to double in size, that is the mean generation time or the doubling time. It can also be calculated if the population doubles, that is T is equal to G. Then, okay, when T is equal to G, then NT is equal to 2N0. Okay. So these 2 and 0, it can be substituted in the equation. Okay. In this equation, you can substitute the NT as a 2 and 0. Okay. So here, K is equal to log of 2 and 0 minus log of N0 divided by 0.301 G. So this is equal to log of 2 plus log of N0 minus log of N0. So the values, it is going to be cut, and this 0.301, it is a log of 2. That's why K is equal to 1 by G. Okay. The mean generation time is reciprocal of the mean growth rate constant, that is a G is equal to 1 by K. This it is a growth rate constant, this it is what? This it is a generation time. Okay, so the rate constant, it is inversely proportional to the generation time, and the generation time, it is inversely proportional to the rate constant, growth rate constant. Okay, now generation time can be calculated from the microbial growth curve. If you want, okay, if you have done the experiment of the growth curve and you want to calculate the generation time, it can be calculated from the microbial growth curve. It is a monoaxial growth curve, or it is going to be called as a normal growth curve. So here, here after the experiment, you have plotted the graph as the time in hours against the number of cells, time in hours on the x-axis and the number of cells on the y-axis. Now here what you observe, that first you are going to observe here lag phase, and then there is a start of the exponential phase, that is the log phase. In the exponential phase, there is an exponential increase in the number of cells. Okay, so by taking the slope, you can calculate the generation time. Now here, as it has been shown here, you are taking the number of cells from the y-axis, it is going to intercepting at the graph, and then you are taking the straight line, okay, and it is going to intercept at the x-axis. In the same way, you are going to take for the second cell number, and you are going to give the intercept at the x-axis. Now the time which is going to be present in between these two, it is going to be a generation time, and here you can say that it is approximately of the 45 minutes. Okay, so from the graph you can calculate the generation time. Now you can calculate the generation time directly from the equations also. Now suppose that a bacterial population increases from 10 bar 3 cells to the 10 bar 9 cells in 10 hours. Okay, this it has been given, and now you have to calculate the generation time and you have to calculate the growth rate constant. Now what is known to you? What has been given in the equation? Okay, in the equation it has been given 10 bar 3 cells. Okay, 10 bar 3 cells, which is the N0, and 10 bar 9 cells, it is a NT, and 10 hours, it is a T. So you can calculate what? You can calculate this K. As you know, the equation for the K is equal to log of NT minus log of N0 divided by 0.301 T. So when you are going to substitute these values in the equation, you are getting the 2 generations per hour. You have calculated the K, okay, 2 generations per hour. And now from this K, you can calculate the generation time. How? You know that the K is equal to 1 by G, or the G is equal to 1 by K. So you know the K now. So you can have the G. How? G is equal to now 1 divided by 2 generations per hour. So this is equal to the 0.5 hours per generation, or the 30 minutes per generation. So if you know the initial cell number and you know the cell number at a given time and the time, at that time you can calculate both of them, generation time as well as the growth rate constant. The second equation here, it is the uh, suppose the generation time of a bacterium, it is a 90 minute, and the initial number of cells in the culture, it is a 10 bar 3 cells at the start of the log phase. Okay, how many bacteria will there be after 8 hours of the exponential phase? Now 90 minute, it is what? 90 minute, it is the generation time, that is the G is equal to 90 minute. And what has been given at the start of the log phase, there are the 10 bar 3 cells. It is nothing but it is a N0, it has been given. Okay, N0 is equal to 10 bar 3 cells, and T is equal to 8 hours. Okay, the T it has been given. Okay, so here first, as the generation time it has been given, okay, that is doubling time it has been given, you have to calculate first what? You have to calculate the K. So the K is equal to 1 by G, you can calculate the, by this equation, you can calculate the K, that is a growth rate constant. And from the growth rate constant, you can calculate the NT by using this equation. Okay, so in this way, you can use the mathematics of the growth to calculate the generation time, to calculate the growth rate constants, also to calculate the initial number of cells and number of cells at a given time. I think you may have cleared the idea. If you like my video, please subscribe my channel and also share my videos with your friends so the knowledge it is going to spread. Thank you.